Okay, so here's a little review with just 3 slides that allow you to check in around some vocabulary and a few aspects of wave characteristics. So on this first slide, you can see 4 waves illustrated. And the first wave, which is down here at the lower left, is a wave that shows you the standard measurement of a wavelength, and they're showing it peak to peak. You can also see that the amplitude is indicated in green. That's the height from the baseline to a peak or the baseline down to a trough. Here I'll shade in an amplitude. There's the amplitude, that much down to the trough. You also see that they have a frequency here being measured of 1 hertz. Now that would be the frequency if this wave was in motion, and we can put it in motion to the right, and we saw 1 full wave cycle go past a point every second. 1 cycle per second is 1 hertz. So remember, a hertz is also equal to 1 per second. On the right, you can see that same wave has been altered, and so in the first case, we have a lambda of x, we have a nu of 4 hertz, and so in this wave, 4 cycles per second, 1, 2, 3, 4, we would see 4 peaks go by every second. The amplitude is said to be y. If we take that same wave and we cut the wavelength in half, we shorten the wavelength, then if the wave's moving at the same speed, we would see 8 wave cycles per second. 1, 2, 3, 4, 5, 6, 7, 8. If we took the same wave and we went back to 4 hertz, but doubled the amplitude, it would look like this third wave. So this is just a good chance to compare different wavelengths and frequencies and see what the wavelength change means to the frequency. If the waves are traveling at the same speed, shorter wavelength means higher frequency. If the waves are traveling at the same speed, higher amplitude doesn't change the wavelength or frequency, it changes the height of the wave or the energy that it has. Okay, so here's our sample calculation. Our key equation that you see up here on the left is v equals lambda nu, or v, speed or velocity, is lambda, the wavelength, times nu, the frequency. And so if I know the wavelength, and that's 1.2 meters, and if I know the frequency, and that's 0.5 hertz, then the simple calculation is that the speed is the wavelength times the frequency, and that would be 1.2 meters times 0.5 per second, or 0.6 meters per second. Now, that same equation can be solved to find the wavelength, lambda is v over nu, or to find the frequency, nu is v over lambda. Now, we do have one other concept that's related to frequency, and that's t, the wave period. So the wave period, which we're using a large T here to indicate, is the inverse of the frequency. So wave period is 1 over nu. So in this case, if I said, hey, the frequency is 0.5 hertz, what's the wave period? 0.5 hertz means that for any given wave, we get through only 1/2 wave cycle per second. If it's 1/2 wave cycle per second, what's the wave period? Well, the wave period is the time that it would take to go through a whole wave cycle, and if we get through 1/2 per second, then 1 over 0.5 is the wave period. The wave period would be 2 seconds. And that makes sense, because if it takes me 1 second to get through half a wave cycle, it would take 2 seconds to get through a whole wave cycle. So wave period is 1 over frequency, and it's also true that frequency is 1 over the wave period, since those are inverse of each other. So here's a slide to give us a little bit of instruction on standing waves and how standing waves are formed by 2 waves that are interfering with each other. And what you can see in the top image, which is labeled A, is you can see 2 waves, which is a red wave and a blue wave, E1 and E2. And we can imagine that they're moving in opposite directions. So imagine that the blue wave is moving to the right, and at the same time, the red wave is moving to the left. If those 2 waves are moving in opposite directions, we can see there will be moments, as indicated here, where they're aligned with peak aligned to peak and trough aligned to trough. And if we were to add those waves up, we would create a wave that was twice as high and twice as low. But as the waves moved past each other, that synchronization of peak to peak and trough to trough would shift, and we would move to the situation that we can see in the bottom in B, where we can see that the blue trough is aligned with a red peak, and that if we add those up, they'll cancel out. and the blue peak is aligned with the red trough. And if we add those up, they'll cancel out. And so if we watch the black wave, which is the summation of the red and the blue, we would see a standing wave, a wave that does not appear to move right or left, but simply goes up and down in place. Now there are two important points on a standing wave that we have named. There are points that make the peaks, and I'm drawing black dots to show the peaks and the troughs. And those are the points that seem to go up and down. They're called antinodes. Antinodes don't seem to be moving right or left. They're simply going peak and then trough, peak and then trough. But there are also points, and you can see them now, the dots that I'm indicating on the baseline with an X through them here and here. Those points don't seem to move off the baseline at all. Those are called nodes. So the nodes, here's a node. The nodes are the points that don't move. Here's a node. And the nodes actually just sit there. Now again, on the lower graph B, let me indicate where the nodes are. Here's a node sitting on the baseline. Here's a node sitting on the baseline. Here's a node sitting on the baseline. So the nodes don't seem to move. So if we imagine a standing wave, we could see a wave where we have one plus another adding up. It's important that to add up, the waves have to have similar wavelengths and frequencies so that they can be resonant. If they have similar wavelengths and frequencies, then the peaks and the peaks can line up. But if one wave and another wave have very different waveforms, we won't get a perfect standing wave because they won't be able to add up and cancel out in a regular pattern. So now here's a quick check for you. What if I asked you, knowing that V equals lambda nu, what if I said, what's the wavelength of a sound note when I know that it has a frequency of 600 hertz? Well, I need to give you some information on that. The speed of sound in air is defined as 340.3 meters per second. So my question is, what is the wavelength of a note that we know to be 600 hertz in pitch? So 600 hertz in pitch is the sound, and the velocity is defined. So why don't you pause this for a moment. You can hit pause and then see if you can solve that, and then come back and we'll give you the solution. Okay, so here's the solution. First, we need to solve the equation for lambda. Lambda equals V over nu. So solved for lambda, velocity over frequency, we plug in our velocity of 340.3 meters per second, and we plug in our frequency of 600 hertz, which is 600 per second, and our answer, which is up here in the right corner, becomes 0.567 meters. The per seconds cancel, and I'm left with this meters, which I should be since I was finding a lambda, a wavelength. Here's another quick practice problem. What's the frequency? What is the frequency nu of a wave with a wave period equal to 0.003 seconds? Well, pause and see if you can quickly figure that, and then we'll come back and see what the solution is. Okay, so here's the solution. Nu is 1 over t. We know the wave period, so 1 over 0.003 seconds, and that should give you 333 per second, or 333 hertz. So that would be the frequency of a wave that has a wave period of 0.003 seconds for a full wave cycle. So here's the last practice problem. A sound wave has a wavelength, lambda, of 0.78 meters. Find the wave period for this sound wave. And remember that V equals lambda nu, and that T equals 1 over nu, and also that the speed of sound is 340.3 meters per second in air. So find the wave period. Why don't you pause it? Just try that for yourself for a moment. Pause it, see if you can make the calculation, and then come back and see what the solution would be. So since nu equals V over lambda and T equals 1 over nu, we start out with nu equals 340.3 meters per second divided by 0.78 meters. That's equal to 436.3 hertz. Now we just need to take that frequency and take the inverse. So we're going to do 1 over 436.3 hertz and see what we get. And that's going to be 0.0023 seconds. So that will be my wave period. So that's a few quick review problems having to do with wavelength, frequency, wave period, and velocity.